The next topic covers kinetics of rigid bodies, that is, the relationship between forces and motion in rigid bodies. Now, it's convenient to conceptualize the motion of rigid bodies and the kinetics of rigid bodies by building on what we learned previously about the kinetics of systems of particles. And we can imagine that a rigid body is just a collection of particles that are all rigidly attached to each other. So if these are a bunch of particles, imagine a bunch of tennis balls or something glued together into some odd shape, forming a large rigid body. And then we can use the concepts from systems of particles to build up our model for the motion. If it has a bunch of forces applied to it, then you may recall from the kinetics of systems of particles that we found we can represent this motion with two equations. One is the sum of all forces acting on all particles in the system was equal to the mass, the total mass of the system, times the acceleration of the mass center. So that leads us to the concept of some mass center. We called it G. And the second equation was the sum of all moments about that mass center was equal to the time rate of change of the angular momentum about the mass center. And so we can use these two equations for the kinetics of rigid bodies, just like we did for systems of particles. So suppose we have a rigid body and it's moving in 3 dimensions. And it's acted upon by several forces. And we can also imagine that this rigid body is comprised of many particles, each particle having a mass of delta m sub I, okay, where I is 1, 2, 3, up to whatever the number of particles may be. Well, first we can consider the motion of the mass center. Suppose this is the mass center, G, and let's also attach a reference frame to G, and we'll call it x prime, y prime, z prime. Well, we know that the motion of the mass center with respect to this fixed frame, call it O, and it's fixed, we can say that the sum of all the forces acting on all of the particles is equal to the total mass of the system times the acceleration of the mass center, as we said a moment ago. And considering the centroidal reference frame G, the sum of all moments about G is equal to the time rate of change of the angular momentum. Okay. Now these equations apply to general 3D motion for any rigid body. Let's restrict ourselves now to motion in a plane and consider the angular momentum. So suppose we have a slab or a rigid body in a plane. In this case it's moving in the xy plane, and again assume it's made up of a bunch of little particles, these p sub i's, each one has a mass of delta m sub I. Now we can obtain the angular momentum with respect to the origin O or with respect to the origin G. And you may recall that there, from kinematics, there are two ways to calculate the angular momentum with respect to the mass center for a system of particles. this is equal to the sum over all the particles, so I equals 1 to n. One of the ways, r prime sub I. One of the ways is to take the moment, of course, about g, so r prime is the position of the particle with respect to g, that's this vector, and we're going to use the momentum calculated with respect to the mass center, so it's v sub I prime, that is the velocity measured with respect to g. There was a second way of calculating angular momentum, which was using the momentum and hence velocity in the absolute frame with respect to O. Using this approach, right, so r sub I prime is the position of a particle, a point on the rigid body, right, with respect to the mass center, and v sub I prime is the velocity with respect to that mass center. But since this particle belongs to a rigid body, we know that the velocity of that particle, or that point on the rigid body, with respect to the mass center, so the prime, is equal to omega cross r. Right, that was just kinetics for rigid bodies we learned previously. So we can use this to write our angular momentum with respect to the mass center. That's an I equals 1 to n. Summing over all the particles. We're still imagining our rigid body as a collection of particles. We'll move away from that in a moment. So now we can express our angular momentum using what we know about the velocity for a point on a rigid body. Now you can verify that this vector, angular momentum vector h sub g, is a vector that points in the same direction as omega. In other words, it will be perpendicular to the plane of motion. Now that is frequently going to be the z direction if we choose to represent the plane of motion as the xy plane. Okay, so this is the expression for angular momentum. And we know that its direction is going to be perpendicular to the plane, and the magnitude of that angular momentum is equal to omega times the sum over r, the r sub I primes squared, delta m sub I. So you might note that this term in the expression for the magnitude of angular momentum you may recall that the definition of the mass moment of inertia of a body about its mass center, we'll call it I, perhaps we'll subscript it with a G just to highlight that, is equal to the sum over all the r sub I prime squared delta m sub I, if you have a bunch of discrete points collected together like that. Or if we were to think of this in the limit as the delta m sub I becomes quite small, and maybe more commonly, the mass moment of inertia is equal to the integral of r squared dm. So what I'm getting at here is that our angular momentum magnitude, h sub g, is equal to I times omega. So that reduced quite a bit. And this is only for plane motion. That's important to remember. We can also say that the vector angular momentum about the mass center is equal to the mass moment of inertia about the mass center times the vector omega, since they're in the same direction. So that's a very important equation when it comes to the kinetics of rigid bodies in plane motion. And all of what we'll be doing for the remainder of this course will be plane motion of rigid bodies. Also remember that this does not apply to general 3D motion. Only valid for plane motion, not for three-dimensional motion. So, the fundamental equations for plane motion, right, of our rigid body, we have a bunch of forces acting on it. Here's the mass center G. And since we're in a plane, we have three equations of motion, scalar equations of motions that apply. First, the sum of all forces in the x direction equals the mass times the acceleration in the x direction. Then we have the sum of all forces in the y directions as the mass times acceleration in y. And then the sum of all moments about g is equal to the mass moment of inertia I times alpha. I think I forgot to point out from our previous slide, if the angular momentum is equal to I times omega, then the time rate of change of that will be equal to I times alpha. And remember, this is the equation of motion that we had previously for general 3D motion. So, these are the equations of motion for a rigid body undergoing plane motion. Those are scalar equations, right? I think it's important to recall that these accelerations pertain to the mass center. Right? And that is the mass moment of inertia about the mass center. Okay? So those three equations of motion are all you need to determine the kinetics, or to establish the equations of motion for plane motion of rigid bodies. We can separate this into some more simple cases, increasing complexity. For example, for a rigid body in translation, right? If it's in translation, then alpha, the angular acceleration, will be 0. The rigid body won't be rotating at all. Its orientation will be maintained, so omega is equal to 0 and alpha is equal to 0. Therefore, the sum of all moments about g is equal to 0. Right? And we're left with the equations of motion are that the sum of all forces in the x direction equals the acceleration in x, times the mass, and the sum of all forces in the y direction equals the mass times the acceleration in y. So for pure translation of a rigid body, those are the only equations of motion necessary. Next, for centroidal rotation, that is rotation about the mass center. Imagine a wheel rotating about an axle at its center, or a gear rotating on a shaft. where the shaft passes through the center of the gear. These would be cases where a rigid body is rotating about its mass center. In this case, the sum of the acceleration of the mass center, right, is equal to 0, and therefore the sum of all forces in both x and y direction are equal to 0. And the only equation left is that the sum of all moments about the mass center is equal to the mass moment of inertia times alpha. So that's the only equation for centroidal rotation. And then finally, we have general plane motion. Where all three equations apply. So the sum of forces in x, mass times acceleration in x. The sum of forces in y is the mass times acceleration in y. And the sum of the moments equals I times alpha. Now remember, in this case, these accelerations relate to the acceleration of the mass center itself. If you want to know accelerations of other places on the rigid body, you find the accelerations of the mass center, and then you use kinematics of rigid bodies that we did previously to find accelerations elsewhere on the rigid body. Okay. A couple of more cases that come up in plane motion for rigid bodies. First is rotation about a point that is not the mass center. Here's a simple example, a bar that's pinned at one end. Like that. And here is the mass center. Well, you'll note that as this bar pivots about the end point, that the mass center itself will follow a circular path. So we have essentially a particle undergoing circular motion, or a point undergoing circular motion. And so what we know about that is we know, remember, whenever anything's moving in a circle, we run two normal and tangential components. So we know that the acceleration can be split into, first of all, the normal component, right, and secondly, the tangential component. And the constraint tells us that the acceleration of, and again, this is the acceleration of the mass center, very important, so let's write it this way, acceleration of gt, just to highlight that fact, is going to be equal to r times alpha. Now r is the distance between the constrained, or the point about which it rotates, and the mass center. Okay? And then the acceleration of g in the normal direction is equal to r times omega squared. This comes from the fact that we know that this acceleration is v squared over rho, the acceleration, the normal acceleration for a particle or point moving in a circle, while the velocity is r times omega, and the radius rho in this case is r, and so that simplifies to r omega squared. Okay? So that's very important to recognize what the accelerations are for this non-centroidal rotation. And then the equations of motion are as follows. The sum of forces in x equals the mass times acceleration in x. Okay? The sum of forces in y equals the mass times the acceleration in y, the same as before. But now for the moment equation, we're going to take the moments about O, that is, the point about which our rigid body is rotating. And that will be equal to the mass moment of inertia about the same point, O, it's different from g, times alpha. Okay. So these are the equations of motion that you will use for non-centroidal rotation. Now note, depending on how you pick your coordinate systems, in this case, if I said this was y and this was x, there would be a relationship between the acceleration in x direction and the acceleration in the normal direction, because they're opposite directions, relationship and the acceleration of y, because of the way I chose my coordinate systems. We'll see more about this when we do examples. Okay. One last case. Oh, one more thing. So very important, the accelerations again, or accelerations of the mass center, but we need the mass moment of inertia about some point other than the mass center. Most of the rigid bodies you'll encounter, you will be able to find the mass moment of inertia about the mass center from tables in your book. Simple things like bars and discs and squares, things and cylinders, stuff like that. There are tables that can give you equations for the mass moment of inertia. But those will be about the mass center. If you need the mass moment of inertia for a point other than the mass center, you need to remember the parallel axis theorem. The parallel axis theorem says that the mass moment of inertia about some point other than the mass center is equal to the mass moment of inertia about the mass center plus the distance between the axis of the mass center and the axis of rotation squared times the mass of the rigid body. Okay? So if you knew the mass moment of inertia about the mass center for this bar, then you could figure out the mass moment of inertia about O by simply adding to that the distance, in this case it's r, squared times the total mass of the rigid body. One last case that we see a lot is rolling motion. So if you have a wheel that's rolling along the ground, right, and there's no slip between the wheel and the ground, okay, then the relationship, there's a fixed relationship between the angular acceleration alpha and the linear acceleration a. And that relationship is that a is equal to minus r times alpha, where r is the radius. Okay. And the minus sign is because of the right-hand rule. For example, this alpha is in the negative direction if y, x. If that's my coordinate system, so to keep the convention of sign, acceleration is in the positive direction. Here alpha is in the negative direction the way I've seen it. That's why we have the minus sign. Okay. So that's an important constraint relation for rolling motion. So that's it for kinetics of rigid bodies. 3 equations. Just like that, with a few special cases that relate these equations to constraints.